Welcome back to Physics 30. This is FI2.6. Force on electric current in a magnetic field. Definition of B, the magnetic field. So last section we looked at a current carrying wire making a magnetic field. And now we'll look at forces involved with a current carrying wire and an external magnetic field. So we have another right-hand rule here to look at to determine the direction of the force on a current carrying wire placed in a magnetic field. So suppose a straight wire is placed in the magnetic field between the poles of a horseshoe magnet as shown below down here, where the vector symbol B represents the magnitude and direction of the magnetic field. So we use the symbol B to represent magnetic field. When a current flows through the wire, experiments show that there is a force exerted on the wire, but this force is not toward one or the other pole of the magnet. Instead, the force is directed at a right angle to the magnetic field direction, and in this scenario, it would be going down. Now, in terms of directions, think of it in terms of what's happening to your page. We have up, down, right, left, and there's two more directions. Out of page, and then we have into page, so to look at the three-dimensional aspect of it. So coming out of the page would look like this. So you can see my pen is coming out of the page, pen is going into the page, up, down, left, right. Okay, so those are the six direction conventions that we're going to be using. If the current is reversed in direction, such as here, it's coming, now in this diagram here, this wire is going into the page. They tried to draw it three-dimensionally, so the pen is going, the current's going into the page, and in this one, the current is coming out of the page like that. And the force is upwards again. No matter what the case though, the direction of the force is always perpendicular to the current and also perpendicular to the magnetic field. Okay? Now, there's a way that we can remember or figure out which direction the force will be by looking at another right-hand rule. So the direction of the force is given by another right-hand rule as illustrated on the figure to the right. So right down here. Orient your hands until your outstretched fingers point in the direction of the current. So the fingers point in the direction of the current. When you bend your fingers, they point in the direction of the magnetic field. So when you bend what I often like to do is to leave my index finger pointing this way and then make your other three fingers point inwards like that. So it kind of looks like a gun shape like this. And then the thumb will point in the direction of the force. So if we apply that to this diagram, so the current is going, now I use my right hand here, right? Because current is represented by positive charges moving. So use your right hand. So the hand is going into the page. As we can see, the magnetic field line is left to right. So I have to turn my hand so that these fingers are pointing left to right. So into the page, pointing to the right. And if you look at what's happening to the thumb is pointing downwards. It's kind of difficult to show this, but into the page, left to right, and you see my thumb is pointing down. So if you're making this symbol with your hand, right angle to this, right angle to both of them, leave your hand orientated like that, and you'll get it. Into the page, left to right, thumb points down. If I look at this, current is out of the page, so coming out at you. Magnetic field is pointing to the right, so coming at you, left to right, and notice what my thumb is doing? Straight up, straight up. So that's how that one works. The other right-hand rule that we used was just to see the magnetic field set up with the wire. Because what we have here is we have two magnetic fields interacting with one another. So the other video's right-hand rule was you grab the current carrying wire. So that's this wire going into the page. I'm going to grab it. Thumb's pointing in the direction of current. Notice that, and my fingers encircle in such a way that shows the magnetic field that the wire makes. So it would look something like this. So on top of the wire it's pointing to the left, below the wire it's pointing, sorry, the top of the wire is pointing to the right, below here. So you can see the magnetic field made by the current carrying wire interacts with the external magnetic field. So the current carrying wire magnetic field and the horseshoe mag's magnetic field combine on the top. They're both pointing in the same direction, to the right, to the right. And on the bottom, to the right, to the left, they cancel out. So we can think of that canceling area is the area that's going to experience the force. Whereas if I look at here, grabbing the wire, coming out of the page, thumb pointing out of the page, fingers encircle the wire. So like that. So you can see that on top it cancels, bottom it combines. So we have that throwing out. Now again, we can use a left-hand rule too. If we have positives going one way, negatives go the opposite way. If you think of negatives as a negative charge, they're opposite, so you use a left-hand rule for that one. Now in terms of symbols, it's easy to see that this is up, this is down, this is left, this is to the right. But how do you represent out of the page and into the page? Like we can either draw a three-dimensional diagram like this, which is somewhat difficult to decipher, so there's another thing that's often done. So if we want to represent current pointing out of the page, so towards you, so think of out of the page as coming out towards your eyeball, okay? We often draw it as a circle with a dot in it. You can think of that as like, if we think of it as an arrow, an arrowhead pointing at you, coming at you, that's what you would see likely. If you want to represent electric current pointing into the page, so going into the page like this, going in, you would see the tail end of an arrow. You would see that part. So it would kind of look like an X. Even though I know arrows technically have three fletchings like that, we could say you have an X. So we could say like an arrow moving away from you. Whereas this, like an arrow moving towards you. So let's take a look at an example. Let's say we have a region here. Let's say we have this. So let's call that current, and we'll say magnetic field is going this way. Okay, so how would we handle that? So current we'll assume is positives, so we're going into the page. The magnetic field is going to be demonstrated by these fingers, which have to be perpendicular to my index finger. So index finger is into the page, these fingers are to the left, and as a result you can see which way my thumb is going. The force is upwards. Okay, so that's how we do that. That's how we represent those types of diagrams and how we figure that out. So go ahead. The assignment doesn't have a lot of questions, but it involves using the right-hand rule and trying to figure out what happens there. So you're given a direction for I, you're given a direction for B. Remember, this points in the direction of I. Leave your hand shaped like this. This points in the direction of B, and then your thumb is the resulting force direction. So we should be able to do the assignment. We'll see you again.